So here's part 2 of the chapter 6 regression inference notes. We just finished the plan step. So once we've stated that we're going to run a linear regression t-test, remember these little b1s are going to follow a t-distribution. We're moving into the do step. So just like the other t-tests that we've run in this class, the do step, we need to report the test statistic, the p-value, and the degrees of freedom. So let's come back to this picture up top. So if we remember from class, we talked about the sampling distribution of slopes. So if I go out and I collect 50 people and I look at their waist and their body fat percentages, those dots might look like that, or they might look like that, or they might look like that. All of those are perfectly feasible outcomes, but they'll return different slopes. Well, if I go out and I ask every single person in the population, let's say the population is all US men, I go out and I ask all of them, so we're talking millions and millions of dots. I go out and I ask all of them, there truly exists some line that fits that best. Now, I don't know what that is, but there truly exists some slope that fits that population distribution best. So that'll be the center of our sampling distribution. So most of my sample slopes should be close to the true slope, but of course it might be a little too steep. So it might be over here to this side, to the right, or it might be a little too flat, so a little over to the left. So that gives us that nice distribution. Keeping in mind this is a t distribution. This is not a normal curve. Okay, so maybe I should have made that a little bit flatter, but that's okay. So my t distribution is just all of the possible sample slopes I could get. Okay. So what I'm going to do is I'm going to calculate a test statistic. So the test statistic is going to be t, right? Because this is a t-test. And just like in the past, it's going to be statistic minus parameter all over the standard deviation of the statistic, which is just going to be the standard error. Well, the parameter I'm hypothesizing is 0, so that would just go away. But in other words, this is just going to be b1 minus beta 1 all over the standard error of the slope. Okay, your calculator will do this, or a computer software will do this, but it's useful to know this general formula right here for calculating test statistics. Whether it's Z or T, the test statistic formula is always the same. That's over on the orangish pink poster hanging over on the string by the window. Okay, so you've got your test statistic, that has to be reported. You've got your p-value, so that's just if I get a t of, let's say this comes out to be 5. Well, how unusual was it to see a t-score of 5? Well, let's come up. So 1, 2, 3, 4, 5. T-curves go out a little bit differently, so I'm not going to do 3 tick marks. But let's just say that this was how many tick marks for this t distribution. So I'm going to ask myself, how unusual would that t-score have been? That's my p-value, so it's the probability of seeing a t-score that or more unusual if the null is true. And we've done p-value interpretations quite a handful of times now, so hopefully that's becoming pretty comfortable. And that's just going to look like probability that t is greater than or less than the test statistic. And that's this value right here that we calculate. Okay, if I wanted to do this by hand, I'm going to do T CDF. So again, that's why this picture is so useful. I've got a curve, I've got a lower bound, I've got an upper bound, and I want to find the area in between. So TCDF, if we jump to our calculator real quick, just as a refresher, we're going to go to second vars, and it's going to be TCDF right there. Lower bound, upper bound, and degrees of freedom. Well, degrees of freedom, we haven't talked about that just yet. So let's go ahead and talk about that now. Again, degrees of freedom are going to tell you how flat or how steep. So is it this steep? Is it this steep? Is it this steep? How steep is that t distribution? Degrees of freedom, we will review all of the different ways to calculate these, but the way we can remember this, when we were talking about single variables, so like how many M&Ms were orange, brown, blue, yellow, etc., it was number of categories -1. Or when we were talking about a single variable t-test, it was n -1, so your sample size -1. Well, now, if we're thinking about this, I have 2. So I have an X group, and I have a Y group. So what I do is I have to take 1 and take 1 is one way of thinking about it. Maybe not the greatest way, but it is kind of tricky to keep all these degrees of freedom formulas straight. It's going to follow degrees of freedom n -2, okay, where n is your sample size. Okay. All 3 of those things need to be reported when possible. I will tell you that the degrees of freedom, sometimes it's just not possible to do. We'll see an example of that in just a moment. Right here for the conclude step. So once you've reported all those values, what kind of decision are we going to make? Well, that just depends on your p-value. That has been the same all semester long. So if the p is low, reject the hoe. So if our p-value is lower than our alpha, or any reasonable alpha, we'll reject just like we have done in the past. Oops. Okay, so for your conclusion, there's going to be a few different pieces. It's going to be a little bit more extensive. We're still going to stick with our 2 sentences to start, but then we'll have to add one more. So let's say first sentence, we reject or we fail to reject the null because the p-value is, and then you would say less than or greater than alpha or any reasonable alpha. Okay, so that would mean we have sufficient evidence that, and then we want to state the null, or sorry, we want to state the alternative in context. Your third sentence, if you can do sentence 1 and sentence 2, you're in good shape, but sentence 3 is going to help on most free response problems. Again, the rubrics kind of change from year to year, but you're going to want to say, so as x variable increases, y variable, what happens to that? Does it increase? Does it decrease? Does it change? Are you not sure? And that just depends on your alternative. So let's look at some of the alternatives. If your alternative is that there is a positive association, you have a positive slope, you're going to be saying that it increases. So if it's a positive slope, you're saying that as x increases, y increases. Well, if your alternative hypothesis is that there is a negative association, that's going to be that as x increases, y decreases. And then finally, if you just weren't sure, but you were just hypothesizing alternatively that there was some linear relationship, then you would just say that b naught, so you're saying, sorry, b1 is not equal to 0. As the as the x variable increases, let's try that again. If your alternative hypothesis is just that there is some linear relationship, so b1 is not equal to 0, then as the x variable increases, you would just say that the y variable changes. Okay. Now, like I said, if you can get those first 3 sentences, you still might be eligible for full credit. It just depends how strong this second sentence is. The second sentence, because that's where you've tied in the context, is going to kind of determine your extra, just how well you understand it. So for step 3, just want to point out that this x variable and this y variable need to be stated in context. Please do not just say x variable and y variable. So for example, a conclusion, if we had run a test for the waist size and body fat percentage example, I would say we fail to reject, let's reject. Rejecting is more interesting. We reject the null because blah, blah, blah. The p-value is lower. We didn't calculate one of these, but let's just pretend. So we have sufficient evidence that there is a positive linear relationship between waist size and body fat percentage. Okay, so I just want to stop right here and point out that what I just wrote right here in green, positive linear relationship between waist size and body fat percentage, that is my alternative in context. So that would have been the alternative, right? I think there's, as your waist gets bigger, your body fat percentage is getting bigger, would have likely been my alternative hypothesis. So let's finish this up. So as waist size increases, body fat percentage increases, and that's it. So just one little elaboration on you understanding what a positive linear relationship means. So it's this little piece right here that needs some elaboration. Okay, so let's see a full example of this. I know that the next page says confidence intervals, but I kind of feel like we're ready to see an example. So we're just going to go ahead and skip down to this section right here. So this section right here, it states that there are two ways to do the do step for regression inference. So tests and intervals, which we're just going to talk about tests right now. If I have the actual data, we'll see an example of that. We're going to go to stat, tests, lin-reg t-test, or t-int on calculator, or we can calculate by hand. You would never do this in the 21st century. It's just not practical. Okay, so if I was given raw data, then I'm just going to open my calculator. I would want to enter all that raw data. So let's see, it looks like I've already got some in here. But I haven't checked the conditions yet, so I probably don't want to run that. But what I would want to do would be stat, tests, and then just run a lin-reg t-test. It's going to prompt you for L1, L2, and then it's going to ask you for your alternative. So do we think beta is what? Do we think it's a negative association? Do we think it's a positive association? Are we not sure? Regression equation would be in there, or it's not necessary, and then you can just press, so if you have the data in there, it'll do it for you, and you would just calculate that. Okay, I don't have an example of that right now. The first example I want to talk about is the more popular example. So primarily on the free response and even in the multiple choice for this chapter, it's how well can you take computer output and interpret those values. So this is really interesting because we haven't, well, I shouldn't say really interesting. This is just a point of discussion where we have values that for this class we will not use, but for other classes I'll talk about a little bit of why you might want to use them in the future. So let's first jump into what we should be familiar with. So if we're looking at the constant, if you think back to the Algebra 1 days, which one of those is my constant? B. B is my constant. Okay, so in the same idea over here, the constant, your coefficient, that number right there, that's going to be your B naught. And I'll go ahead and just write that instead of typing it. So B naught. That number right there. Okay, and this number right here, so let's go ahead and just talk about context right now. It looks like the response attribute, so the response variable, is the age of the wife. And so that's going to be the y. We're trying to predict the age of our wife based off of, well, down here it says predictor, that's age of husband. So age of husband, so we're thinking just in our heads that as husbands get older, the age of their wife also gets older. Okay, but we know that's not always true. In the case of many celebrities, some males get older and start dating younger wives, but that's what gives us the interesting scatter plot rather than just a straight line. We've got some people that won't follow that perfect pattern. Okay, so what's that value? The age of husband. So this is our explanatory variable, the age of husband. Let me erase this. Age of your husband, that is X. Age of wife, that is Y. Okay. So down here, the coefficient, that number in front of X, the age of the husband, that's going to be our slope. And our slope is B1. Okay, so we've got that now. B naught, B1, and we can actually see that if we highlight, let's see, B naught, we see that right here, and B1, we see that right here. And what the computer has done for us, which it will not always do, and you can't guarantee it's going to do it on the AP test, right here it has age of wife, so that's Y. It's gone ahead and it's written Y hat equals B naught plus B1X. That's what this whole thing right here is saying. Oops. Okay. So go ahead and clear that out because we don't need that necessarily. All right, my standard error, my t statistic, and my p-value. It's going to give that to us for both b naught and the slope. Okay, well, that's where things, like I said a couple minutes ago, that's where things get kind of interesting and maybe in a way not interesting. So let me explain what I mean by that. The numbers up here, this coefficient, this standard error, this t statistic, so this coefficient, this standard error, this t statistic, this p-value, are all referring to my y-intercept. So thinking about that in context, if I want to talk about the y-intercept, well, I'm talking about the age of the wife if the age of the husband is 0. Okay, well, that just doesn't make any sense in real world context. Is it something we can calculate? Sure, and it's something that your computer did calculate. Those are those values. But it's not something that we as people are really concerned about. The same would be said for the waist example. So these values can be calculated, these values right up here, can be calculated for the y-intercept for the regression line for that waist by body fat example. But what would those numbers be referring to? They would be talking about if the waist was 0 inches, what would the body fat percentage be? Well, hopefully you're following along the context because that also wouldn't be possible. It's not something we really care to calculate because it doesn't make any sense to the consumer or your boss or the researcher who's crunching these numbers. And then finally, the same can be said for the baseball example we just did. So for baseball, we're talking about pick numbers. All of these numbers across the top, if this was the baseball example, would be referring to the person that was picked 0, the zero place picked person. So again, that doesn't make any sense in the context of the problem. So typically, I won't say always, but typically what you can do when you're looking at constant is you're not going to look at these. Okay. So now that we've got those out of the way, let's identify the rest. That's my standard error. This is my standard error of, let me change colors. If you guys would like, you can go over to the team baskets by the window and pick up colors if you want to try to color coordinate your table. I know this is a lot of writing in such a small space. This value right here is my standard error of x. Oh, sorry, for the B1. So this is the standard error for the slope. Okay. This next value over here, my t statistic, you might have guessed it, that's my t. If I'm running a test, that's my t. That needs to be reported. And then finally my p-value, well, that's just the p-value you want to report. And all of those are fairly straightforward. The only thing we have to be careful of is there's a standard error for the y-intercept, and there's a standard error for the slope. There's a t-statistic for the y-intercept and a t-statistic for the slope. A p-value for the y-intercept and a p-value for the slope. But the y-intercept is very, very rarely something we care to talk about. So that's kind of what I meant about interesting and not interesting. Interesting because it's something that's like strange and abstract about statistics, and most things that we've talked about in this class are not abstract, but not interesting because it's not practical. All right, and then finally, if we want to just look down at these bottom 3 numbers here, r squared, we talked about that. It's denoted that way. R squared, I'll say this and we'll practice it a couple times interpreting, especially as we move into review. This is the amount of variation in y that is explained by the variation in x. So for this example, it's the amount of variation of age of wife that's explained by the variation in age of husband. That's your r squared. And finally, the last value we're going to talk about from this table is going to be the standard deviation of error. That's 3.95, and that is S sub E, the standard deviation of errors, or the standard deviation of residuals. That is very different from the standard error. The standard error is referring to an estimate of a standard deviation, and the standard deviation of error is referring to how much do the dots spread out from the line. Okay, so software is a pretty powerful tool, and it's going to save you from doing a lot of work, but you do have to put the effort in to figure out what all of these values are telling you. Okay, so depending on how many times you had to pause to stop and write, or stop and get a calculator, or what have you, you may be ending before we get to finish an example, but I'll go ahead and stop the video right here, and I'll continue with part 3 of this note in another video. If you have time, please start that 3rd video. If you run out of time, just go ahead and know that we will go over the example and anything else that you don't finish when I'm back tomorrow.